So we have come to theorem 6.2 now. In this, a positive integer n is given and its prime factorization is given, and n of course is greater than 1. And we also understand that these primes pi are all distinct and these ki's are positive integers. If any ki is 0, there is no point writing that corresponding power because it would be 1. Okay, so with this given, tau of n, the number of positive divisors of n would be this product. You add 1 to each exponent and you take the product of those quantities. That will be equal to the number of positive divisors of n. And the sum of positive divisors of n, sigma of n, has this formula, where again for each such prime we get one factor here in this product. And for example, the one corresponding to P1 is this, P1 to the power K1 plus 1 minus 1 divided by P1 minus 1. This might remind you of the sum of a geometric series, a finite geometric series. Actually, that's how it arises. I mean, that is why it looks like this. So it will become clear when we see the proof. So let's now go to the proof. So here's the proof. This is how the proof starts. The proof starts by recalling that recent theorem that we went through, where we characterized all the positive divisors of a positive integer. In our case, for our n, the positive divisors of course are going to look like this, where those primes will be there with some exponents. And for each I, the exponent ai can be 0. Okay, although the ki's are positive, but ai is allowed to be 0 because it's not necessary for the prime pi to be present in every positive divisor. That's why ai can be 0. But ai can at most be ki, it cannot be greater than ki. Alright, now for each such I from 1 through r, the exponent ai can be chosen in ki plus 1 ways. With all these values available for ai, how many possibilities are there? Starting from 1 to ki, there are ki possibilities, and you include 0 also, you get ki plus 1 choices for that single exponent ai. Similarly, you can choose all the exponents, and these choices are independent of one another. So the total number of ways of choosing all these AIs is this product. So you apply a little combinatorics here. So that many positive divisors of n will be there. And one more thing is clear, that for distinct choices of these AIs, you are going to get distinct positive divisors d. So the number of positive divisors is precisely this number, and that is your tau of n. So that is part A. Next, let's go to part B. Well, I should have written A here. Let me write it now. Now in part B, we have to prove that the sum of the positive divisors is this. So let's see how that can be achieved. The proof of part B starts by considering this product. Let's see what the product is. The product has r factors. Okay, this is the first factor, this is the second factor, and so on. This is the rth factor. The first factor involves only the prime p1, and you can clearly see that it's a geometric series, and it starts with 1 and then p1, p1 square, all the way up to p1 to the power k1. It's the sum of all these things. A similar, the second one is similar sum, but this involves p2. And the last one, like that, involves pr. Now the observation about this product is that if one carries out the multiplication fully, there will be many terms and it will ultimately be a large sum. In that sum, every positive divisor of n appears exactly once. you can see for yourself. For example, among all the many possible positive divisors of n, 1 is also a positive divisor, and that 1 will be obtained by multiplying all these 1's. So when you do the multiplication fully, one of the terms in that large sum will be 1, and that will be obtained by multiplying all these 1's. Another positive divisor is n itself, and n is obtained by multiplying these last terms, all of them. So exactly one term will be equal to that product, so that means n is also present here. Like that, it's not very difficult to see that every positive divisor of n will appear in this sum somewhere. When you carry out the multiplication, you get that sum. In that sum somewhere, that positive divisor will appear, and it will appear exactly once. If you want another example, say you can consider the positive divisor p1 square. p1 square divides n, assuming that it really divides n, okay. Where will p1 square appear in this multiplication? p1 square will appear in that term. It will be equal to that term, which is obtained by multiplying p1 square and all the other ones. Obviously, in the multiplication that will happen somewhere. So like that, we get all the positive divisors of n in that sum after you do the multiplication precisely once. So obviously, this itself is the sum of all positive divisors of n, and that is just our sigma n, sigma of n. And finally, you just note that you can write a compact expression for this geometric series, which is your school formula. If you add all these pi's, powers of pi's up, what are you going to get? If you have started with 1 and then you went like this, 1 pi square and so on up to pi to the power ki, then the formula is pi to the power ki plus 1 more than the last exponent, minus 1 divided by pi minus 1, common ratio minus 1. So you replace all these things by these compact expressions and you get what you wanted to get. So that is the proof. So with the help of the product notation, we can express those formulas even more compactly like this. So you understand that this capital pi, just like capital sigma denotes summation, capital pi denotes product. So this notation indicates that we are looking at the product of terms which are of the form ki plus 1. And the variation of I is shown here below that product symbol pi. Just like that sigma is called summation, this is called product. Instead of writing inequalities like this, you can write I equal to 1 to r, just like you write sum in summation notation. Like that also you can write. Similarly, the sigma of n is the product of terms of this form where I varies from 1 to r. Now let's see an example of these two formulas at work. In this example, we have taken n to be 180, and this is the prime factorization of 180, 2 square times 3 square times 5. So according to our formula, tau of n will be obtained like this. You add 1 to each of the exponents and then you take their product. So 2 becomes 3, this 2 also becomes 3. So 3 times 3 is 9, and here we have a 1, so 1 becomes 2, 9 times 2 is 18. So 180 should have exactly 18 positive divisors. And we can see the positive divisors of 180 here. These are the positive divisors. So let's count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Yes, so it's matching. And then we of course also have sigma of n, the sum of these divisors, which according to our formula looks like that. Okay, so and it turns out to be 546. So you can do one thing. You can use your calculator application on your smartphone or whatever, wherever you get a calculator. You do the sum and you see if you really get 546. Next, we are going to see that besides being able to say how many positive divisors n has and what their sum is, we can also say something about what their product is. Again, in terms of these functions, actually tau of n. So let's see that. Okay, so this is the result. Say n is a positive integer, then the product of all positive divisors of n equals this power of n to the power tau of n divided by 2. So what you do, you calculate the number of positive divisors of n, divide that by 2 and then raise n to that power. That will be equal to the product of all positive divisors of n. Let's see how we can prove this. So the proof starts by considering any positive divisor of n, let's call it d. Then n will be equal to d times d prime for some positive integer d prime, and as such d prime will also be a positive divisor of n. Now if you vary d over the set of all positive divisors of n, then you are going to get tau of n number of equations that look like this, where the left hand side is constantly n, but the right hand side changes as d changes, and accordingly d prime also changes. And say then what you do, you multiply all such tau of n number of equations. Then the left hand side will be this power of n to the power tau of n, and the right hand side, if you rearrange things a little bit, instead of writing the factors like d prime, d prime, you collect all the d's together and make a product out of them. So it is the product of all positive divisors d of n. But then simultaneously on this side you have those d primes. So their product also you collect. But now what? Now where do we go from here? Let's see. So here's the argument. As d varies over the set of all positive divisors of n, d prime also does the same thing. So does d prime. And for our better understanding, I have taken a small example to show what happens when we take a concrete positive integer, say 6. We start by considering the smallest positive divisor of 6, which is 1. So if you write 6 as in that form, n equals d times d prime. So here d is 1 and accordingly d prime is 6. Then you go to the next positive divisor of 6, 2. 6 is 2 times 3. Here d is 2, d prime is 3. Then you go to the next positive divisor, which is 3. 6 is 3 times 2. Here d is 3, d prime is 2. And finally, there is one more positive divisor, which is the largest, that is 6 itself. So in this equation, d is 6 and d prime is 1. So as d varies over the set of positive divisors of 6, d takes these values 1, 2, 3 and 6. But simultaneously d prime also does that same thing in the opposite order, 6, 3, 2, 1. So if you take the products of these quantities, on one hand you have the product of the d's, 1 times, 2 times, 3 times, 6. On the other hand, you take the product of the d primes, 6 times, 3 times, 2 times, 1. They are the same. And that is why these two things are equal. So on this side, you have the square of this. Now we are almost there. So let's complete it. So using this equality in that equation, we get this. This side is the square. So then you take square root on both sides, and I have written this on this side and this on this side. So that's how you get the fact that the product of all the positive divisors of n equals this. Now if you think about this quantity, it may confuse you. for one reason. There is actually no guarantee that this tau of n, number of positive divisors of n, will always be an even integer. If it is not an even integer, what will happen to this exponent? It will not be an integer. And so then how will this power be an integer always? However, it is the product of all positive divisors of n, so it should be integer. You know that this will be an integer because there is no gap in the proof. But let us see one particular example where this really becomes odd. Tau of n becomes odd. Let's see what happens in that case. So here is that example. In this example, our n is 16, which is 2 to the power 4, that is its prime factorization. And so by the definition, by the formula for tau of n, it will be 4 plus 1, that is 5. So here n is odd. So the product of all the positive divisors of 16, according to this result, should be 16 to the power 5 divided by 2. Luckily, 16 is a perfect square. It is 4 square. So this becomes 4 to the power 5 and it is 1024. So are we always going to be saved like this? Whenever tau of n is odd, our n actually should be square. That's the case in fact. And we are going to address it fully in its general form later. So let's just end this video here itself, and tomorrow of course we have our upload. And I forgot as usual completely what we have tomorrow, but whatever it is we will see. So see you tomorrow. Until then, this is me, Lucifer, from a mathematical room. Have a nice day.